Welcome back to the Deep Dive. It is Tuesday, February 17th, 2026.
Hello again.
And today we are going to get into the weeds. And I don't mean the fun anecdotal weeds. I mean the mathematical, structural, the how do we actually fix AI weeds.
Which are the best kind of weeds, if you ask me.
Spoken like a true engineer.
Okay.
Look, here is the premise for today. We are, I think it's fair to say, living in the golden age of LLMs.
Without a doubt.
We have models that can write sonnets, they can debug Python, they can pass the bar exam. But, and this is a massive but that keeps researchers awake at night, these models still struggle desperately with a specific type of data structure.
Right. We are talking about structured chaos.
Structured chaos, I like that. Specifically, we're talking about attributed graphs.
Yes. And before you, the listeners, tune out because you heard the word graph, let's be really clear.
Please.
This is the structure of the real world. It's not some abstract math concept.
Exactly. I always picture that meme. You know the one Charlie Day from It's Always Sunny in Philadelphia? He's in the mailroom, eyes wide, hair's a mess, and he's standing in front of this corkboard that's just covered in papers.
Oh, yeah.
And there is red string connecting everything to everything else.
The Pepe Silva board.
Yeah.
That is the perfect visualization of an attributed graph.
It's perfect, right. So the nodes are the papers, the photos, the receipts, the frantic notes. Those have text on them, the text attributes. The edges are the red strings connecting them. That's the structure. Now, here's the problem. An LLM is a genius at reading the notes. It can analyze the text perfectly.
It'll tell you everything that's on those scraps of paper.
But it is surprisingly bad at understanding the shape of the red string.
It sees the content, but it misses the context of the web. And today, we are dissecting a paper that claims to solve this.
Okay, let's hear it.
It's titled To-Retriever, Tree-Based Hierarchical Retrieval Augmented Generation for Textual Graphs. It's by Wei et al., just published at TreeAI 2026.
T-Retriever. It sounds like a specialized dog breed. Or maybe a dinosaur.
It stands for tree retriever. And the name, well, the name gives away the game.
How so?
They're proposing a paradigm shift. The best way to understand a complex graph isn't to treat it like a graph at all.
Okay.
It's to turn it into a tree.
From a web to a ladder. Now, I have to be honest, when I first read the abstract, I was skeptical. I mean, graphs are complex. They're cyclic. They're messy things.
Sure.
Trees are rigid hierarchies. It feels like we're dumbing down the data. Are we just taking a chainsaw to the red string and hoping for the best?
That is the exact right question to ask. And the answer, the whole magic of this paper, lies in how they build that tree.
Okay.
They aren't just hacking away at the edges. They are using a concept from, like, 1940s information theory entropy to mathematically prove that they are preserving the information while simplifying the structure.
Okay, that's a bold claim.
Okay.
So here's our mission for the next hour. We're not just going to nod along and say, good job. We're going to tear this methodology apart.
Let's do it. We need to understand the mechanics.
We're going to look under the hood.
Exactly.
We're going to break down this entropy metric, which sounds like the secret sauce.
It is.
We're going to walk through the adaptive compression encoding, which is how they actually slice the graph. And we're going to look at the retrieval pipeline, which apparently involves graph neural networks acting as translators.
It is a fascinating architecture. And you're right. It really does try to bridge the gap between, say, a vector database and a knowledge graph.
So let's start at the beginning.
Huh.
The problem. Why are graphs so hard for LLMs? We have RAG, Retrieval Augmented Generation. We have GraphRag. Why isn't that enough?
Well, let's define the gap. Standard ARG is great at semantic search. You ask a question, it finds documents with similar words.
The vector search.
Pure vector search.
So that's just reading the notes on the corkboard. It's ignoring the string completely.
100%. Then you have knowledge graphs. These are great at structure. A is connected to B, but traditionally, they aren't great at nuanced text.
All right, they like strict labels. Person A knows you're person B. Very rigid.
Super rigid. So we have attributed graphs, which try to do both. A social network is the classic example. You have people as nodes, friendships as edges.
But every person has a biography, a post-history, a distinct voice. Those are the text attributes.
Exactly. Or a citation network. Or a legal case database. Now, the current state of the art for handling this is something called community detection. You might have heard of algorithms like Leiden or Louvain.
We've heard of them. They're clustering algorithms, right?
Yeah.
They find the neighborhoods in the city.
In theory, yes, that's the goal. They look at the topology, the red strings, and say, hey, these 20 nodes are all tightly connected to each other, so let's bundle them into a community.
Which sounds logical. I mean, if you want to summarize a graph, grouping the tight-knit communities seems like the right first step.
It is the right first step for structure. But here is the flaw. And it's what the T-Retriever paper identifies as the GraphRag bottleneck.
Okay.
These algorithms are blind to the text.
Wait, really? They don't read the notes?
Yeah.
At all?
No, Leiden and Louvain are purely topological. It's like organizing a library based entirely on which books are touching each other on the shelf.
And completely ignoring the titles.
Completely. They don't look at the titles, the authors, the genres, nothing. Just physical proximity.
That seems wildly inefficient. So if a cookbook falls over and touches a sci-fi novel, the algorithm says, these are now in the same genre.
Precisely. It creates what the paper calls the semantic disconnect. You get clusters that are structurally sound, they are connected, but semantically, they're just a mess.
So you have a cluster containing lasagna recipes and alien invasions.
And when you feed that cluster to an LLM and say, summarize this community for me, what's the LLM supposed to do?
It hallucinates.
It has to. It tries to bridge the gap. It says, the aliens are eating lasagna.
Which is funny, but completely useless if you're trying to do medical research or legal discovery.
Exactly. And there's also a second problem with standard GraphRag. Rigid quotas. Many of these systems are built bottom-up. They say things like, okay, every cluster must have exactly 10 nodes, or we need to compress the graph by 50% at every single layer.
So it's like forcing a round peg into a square hole.
Yeah.
You're just imposing this arbitrary mathematical quota on what might be very organic data.
And that damages what they call the local structure. You might split a natural group of 15 people into two groups of 7 and 8 just to fit the quota.
And in doing that, you sever the vital connections between them.
You break the very community you were trying to find.
So we have blind librarians organizing books by size, and we have managers forcing teams to split up just to make the org chart look symmetrical. That is the status quo.
Sadly, yes. That is the community detection trap that this paper is trying to escape.
Okay, enter T-Retriever. The paper calls for a paradigm shift, from graph-based retrieval to tree-based retrieval.
This is the high-level conceptual leap. A graph is a maze. It's cyclic. You can go in circles forever.
A mess of red string.
A total mess. A tree is a hierarchy. It is a root, branches, and leaves. It is a corporate org chart. It's clean.
Okay, let's stick with the org chart analogy. I like that. You have the CEO at the top, that's the root.
Right.
Then VPs, then managers, then the individual employees at the bottom. Those are the leaves, the original nodes.
Exactly. T-Retriever wants to take that messy, chaotic social network and reorganize it into a clean org chart. But, and this is the critical differentiator, it builds it top down.
Top down. Why does that matter so much? I mean, most things I build bottom up. I lay the bricks first before I put on the roof.
Think about the previous methods, like a popular one called Raptor.
Okay.
Raptor works bottom up. It takes individual text chunks, it glues similar ones together into small clusters, and then it glues those smaller clusters into bigger clusters and so on.
So it's like trying to build a house by just gluing bricks together without a blueprint.
Or trying to form a government by just letting neighbors talk to neighbors. You end up with these Frankenstein clusters. They make sense locally. I like my neighbor. We have a lot in common.
But they don't necessarily fit into a coherent global picture.
Exactly. You get a chaotic favela instead of a designed skyscraper.
Okay, I see that.
T-Retriever does the opposite. It starts at 30,000 feet. It looks at the entire graph, millions of nodes, and asks one question.
What's that?
What is the single best way to slice this entire universe into two meaningful parts?
Strategic division.
Strategic division. It's a classic divide and conquer strategy. And the inspiration for how it divides comes from Claude Shannon.
Shannon, the father of information theory. I saw Shannon-Fano coding mentioned in the paper. Now, I have to put the brakes on here for a second.
Look here.
We're throwing around the word entropy, and I feel like in AI, that word gets abused. It usually just means noise or randomness.
It's become a bit of a buzzword.
It has. But the authors are citing Shannon-Fano coding. That is foundational stuff from the 1940s.
Yeah.
How are they actually applying a data compression theory to a 2026 graph neural network?
That is the crux of the paper. You have to go back to Shannon's original definition. Shannon defined entropy as the uncertainty inherent in a variable. Or you can think of it as the minimum number of bits you need to encode a message.
Right. If a message is totally predictable, like a string of all zeros, entropy is 0, there's no surprise.
Exactly. High surprise equals high entropy. Now let's map that to a graph. T-Retriever looks at the graph and asks, how much surprise is there in the connections, the structure, and how much surprise is there in the text, the semantics?
Okay, let's separate those. Take the structure first.
Yeah.
How do you measure surprise in a red string?
Technically, they use a random walk model, but here's the intuition. Imagine you are standing on a node. If you close your eyes and take a step along a random edge, how uncertain is your destination?
Okay, if I'm in a tight clique of friends, a real community,
Yeah.
I'm probably going to land on another one of my friends. Low uncertainty.
Correct. That's low structural entropy. But if you are a hub node connected to 1,000 random people across different groups, your destination is highly uncertain, high entropy.
So the algorithm wants to find slices in the graph that minimize this uncertainty.
It wants to trap the random walker inside the cluster. It wants to create groups where the connections are predictable.
Okay, so that handles the topology. That essentially recreates the community detection part we already said wasn't good enough on its own.
Yeah.
So how does the semantic entropy fight against that?
This is where it gets brilliant. They treat the text embeddings, the vector representation of the node's content, as a Gaussian distribution.
A bell curve of meaning.
A bell curve of meaning,
Right.
right. Imagine every node's text is a point in a big multidimensional space. If you group chair, table, and sofa, those vectors are all clustered together.
They're close.
The spread or the variance of that bell curve is really tight. That is low semantic entropy.
But if I group chair with tax lawn, banana,
The vectors are pointing in completely different directions. The bell curve flattens out like a pancake. High variance, high entropy.
so the algorithm has a minimization problem. It's trying to find a partition that does two things at once.
Mm-hmm.
It needs to keep the random walker trapped, which is the structure part,
Mm-hmm.
and other day it needs to keep the vector spread tight, which is the semantics part.
Precisely. And they combine these two into a single metric. Entropy, semantic-structural entropy.
It sounds like a tug of war. I mean, sometimes your friends, your structural connections aren't talking about the same things as you, the semantics.
It is a tug of war, and that tension is where the magic happens. The paper describes a phenomenon they call the catalytic effect. This was one of the biggest aha moments for me when I was reading it.
The catalytic effect. It sounds like something from chemistry class.
It is a great metaphor. Imagine you have two people in a company. Let's say one is in marketing, one is in engineering.
Yeah.
Structurally, in the company org chart, they are far apart. They don't sit together. They don't report to the same boss. A purely structural algorithm would almost certainly separate them.
Right, different departments.
But maybe they are both secretly working on the same stealth project. Let's call it Project X.
Yeah.
Their emails, their documents, they're full of the same code words, the same technical jargon.
So semantically, they're identical.
Exactly. So the semantic entropy part of the equation desperately wants to pull them together. When you combine them in the SOF formula, the semantic similarity acts as a catalyst.
It overcomes the structural distance.
It pulls these distant nodes together. But here's the magic. To make that group structurally sound, to lower the overall entropy, the algorithm realizes it needs to include the nodes that lie between them on the graph.
The bridge.
The bridge. It pulls in their project manager, the one who coordinates between marketing and engineering.
Oh.
Suddenly, you have formed a new cluster that represents the Project X team. You wouldn't have found it by looking just at the org chart, and you wouldn't have found it by looking just at keywords. You needed both to find the true functional unit.
That is really cool. So it sacrifices a little bit of structural purity to gain a huge amount of semantic coherence, and in doing so, it reveals the hidden backbone of the organization.
That's a perfect description, and the sauce on entropy is the compass. It's the rule that guides every single cut the algorithm makes. It ensures that every branch of the tree represents a genuine concept that is grounded in the actual connections of the data.
Okay, so we have the philosophy, which is top-down,
Right.
and we have the compass, the S entropy. Now I want to see the machine running. I want to visualize the construction. Let's simulate this.
Let's do it.
Imagine we have a massive data set of legal cases. 100,000 court documents. Some cite each other. Those are the edges.
Yeah.
And some are about murder. Some are about tax fraud. That's the text.
Okay, good example.
How does T-Retriever build the tree?
Phase 1 is the encoding tree construction. It starts with step 1, the partition operation.
We start with the root node. All 100,000 cases. It's a giant mess. High entropy.
Right. The algorithm looks for the biggest, most meaningful fault line. It essentially runs a customized binary clustering. It's asking, If I had to split this entire universe into just two piles, pile A and pile B, which split would give me the biggest drop in siren entropy?
So maybe pile A becomes criminal law and pile B becomes civil law. That seems like a logical first cut.
Ideally, yes. But remember the catalytic effect. Maybe there is a huge set of civil fraud cases that consistently cite criminal fraud cases.
Okay.
The Esper entropy might decide to group all fraud cases, both civil and criminal, together in pile A and something like violent crime in pile B. It prioritizes the story and the data over the rigid legal category if the text and connections support it.
Okay, so we make that first split. Now we have two nodes at level 1 of our tree. Then we just recurse.
We recurse. We look at the fraud pile and we split it again. Maybe this time it's into corporate fraud versus individual fraud. We keep going down, dividing and conquering, making the groups smaller and more specific.
But this is where top-down strategies usually fail, right?
Yeah.
You get what I call the orphan problem. You make a split at the top, and suddenly two cases that really should be connected are separated forever because they just happen to end up in different buckets at level 1.
That is the classic risk. Absolutely. And that is why step 2. The preen operation is not just a cleanup step, it's a critical correction mechanism.
Okay, so what's it doing?
The authors use something called the minimum description length principle here, or MDL.
MDL. That's essentially Occam's razor for code, isn't it?
Yeah.
The simplest explanation is the best.
Exactly. The algorithm looks at a split it just made and asks a simple question. Is the cost of describing this new layer of child nodes cheaper than just describing the parent node as a whole?
In our org chart analogy, this is like asking, do these middle managers actually do any real work, or are they just passing messages?
Perfect analogy. Suppose the algorithm split corporate fraud into bank fraud and insurance fraud. But when it looks at the text in those two new piles, they're incredibly similar, and the connections between them are still super dense.
The entropy barely dropped.
The entropy barely dropped. The split didn't really buy us much new information, so the prune operation triggers.
It realizes the split was artificial.
It says, nope, bad split. It deletes the children bank fraud and insurance fraud and pulls all those individual cases back up to the parent level. It says, no, keep this as one coherent group called corporate fraud.
So it prevents oversegmentation. It ensures that every layer of the hierarchy represents a truly meaningful increase in resolution.
A meaningful simplification, yes.
Okay, so we are slicing and we are firing the useless middle managers.
Yeah.
Go to step 3, the regulating operation.
This deals with what you could call the ladder problem. Imagine one branch of your legal tree goes really deep. You have fraud, corporate bank, Enron-specific emails. That's 5 levels deep.
And then another branch involves some weird, unique case that doesn't fit neatly anywhere. Let's say murder case X. That's only 2 levels deep.
Now you have an unbalanced tree. An LLM trying to navigate this will get dizzy. It expects a consistent level of abstraction at each depth. If it knows that level 3 is specific types of crime, it shouldn't suddenly encounter a raw, unprocessed court transcript there.
It breaks the semantic zoom. It's like zooming in on a map and suddenly hitting a high-res satellite photo while the rest of the map is still showing political boundaries.
That's a great way to put it. So the regulate operation is like a quality control step. It scans the tree and detects these short branches. If a node at level 2 links directly to a leaf, but the rest of the tree goes all the way to level 5, it inserts dummy nodes, or placeholder clusters, to fill the gap.
It's padding the hierarchy to make it even.
It forces the structure to be uniform. This seems trivial, but for the retrieval phase that happens later, it is absolutely vital. It guarantees that if I ask to search at level 3, I am getting level 3 concepts across the entire knowledge base.
Okay, so after partition, prune, and regulate, we have a skeleton. We have a balanced, meaningful tree structure. But the nodes, the managers in our org chart, they're empty. They're just containers.
They are, and that leads to phase 2, indexing. This is where we fill those containers. We need to give the managers a job description.
And this is where the generative part of AI finally comes into the picture.
Yes. For every single non-leaf node, every cluster we created, the system takes the text from all its children and feeds it to an LLM.
It just concatenates it all.
Essentially, yes. It bundles it up and asks the LLM a simple prompt. Summarize what these children are about.
So if the children are Enron email 1, Enron email 2, and Enron email 3, the LLM might write a summary like, this cluster contains internal communications regarding the concealment of corporate debt.
Correct. And then, and this is the vital last step of indexing, it takes that generated summary and embeds it into a vector. So now the tree doesn't just have structure. It has searchable meaning at every single level. The top of the tree has vectors for broad concepts like corporate malfeasance. The bottom has vectors for specific details, like one particular email.
It's a fractal index of the graph's knowledge.
A fractal index. I like that. That's exactly what it is.
Okay, we have built the machine. The paper mentions this takes time. I think it's at about 7 hours for a massive book graph.
It's an offline cost, a one-time payment. You pay it once to organize your entire library from scratch.
But then you can search it millions of times instantly.
Exactly.
So let's search it. Section 5. Retrieval and generation. I am the user. I come to this T-retriever system and I type in a query. Find me legal precedents for wire fraud that involve offshore shell companies.
Okay.
How does T-retriever hunt for the answer?
This is where it does something really clever, and it diverges from a standard tree search. In a normal file system, you'd start at the root, you'd pick a folder, you'd open it, pick a subfolder, and so on.
It's a directed path down the tree.
Right. Which is slow. And more importantly, if you pick the wrong folder at the top, say you accidentally click tax law instead of criminal law, you never find the answer. You're lost.
The end.
Exactly. T-retriever doesn't do that. It takes the entire index we just built, the summary for the root node, the summaries for all the level 1 nodes, all the level 2 nodes, and all the actual text from the leaf nodes.
And it does what with them?
It flattens them. It puts them all in one massive single vector space.
Wait. So it treats the table of contents and the chapter text as equally searchable.
Yes. It runs a global approximate nearest neighbor search across everything at once, and this is the key. It retrieves the top K most similar matches regardless of where they sit in the hierarchy.
So for my shell company query, it might grab a level 3 cluster summary called corporate shell structures, and at the same time grab a specific level 5 case file titled United States v. Smith.
Correct. This is the multi-resolution power of the system. It gives you the general context. ND is the specific granular example in one single scoop.
That is smart. It completely avoids the tunnel vision problem of a classic decision tree search.
It does, but, and here's the twist, it doesn't just hand that text to the LLM. If it just gave the LLM the text, we're back to basic RAG. We've lost the red string again.
Right. We did all this work to understand the connections. We need to use them.
Step 3 is subgraph extraction. T-retriever takes those nodes it just retrieved. Let's say we found 5 relevant nodes from different parts of the tree, and it looks back at the original graph. It pulls up the floorboards.
It finds those 5 nodes in the original mess of red string.
And it extracts the induced subgraph. It grabs those nodes and, crucially, any edges from the original graph that connect them.
So it reconstructs the mini-web for just the relevant information.
And it feeds that mini-web into a graph neural network, or GNN. Now, the paper specifies they use a generic GNN encoder, but its function is critical. The GNN looks at the topology of that little subgraph, who is central, who is a bridge, who is an outlier, and it compresses that structural role into a set of what they call structure tokens.
Wait, structure tokens. Explain that. So the LM isn't just reading English anymore.
It's reading English plus a mathematical hint. Think of it like this. The prompt to the final LLM looks something like, here's the text summary. And by the way, here is a special vector signal that tells you this node is a hub that's connected to these 3 other nodes.
So it's translating the shape of the graph into a language the LLM can feel or understand intuitively.
Exactly. They call it textualization combined with structural encoding. It prevents the LLM from hallucinating relationships. It doesn't have to guess if case A cites case B. The GNN signal explicitly confirms it.
So the final pipeline is query Lenimage multi-resolution, cert battle soy subgraph extraction, Dage's GN encoding exception, final answer.
It is a complex pipeline, but you can see how it solves the original problem. The LLM gets the text, which is the semantics, and it gets the confirmed connections, the structure, all presented in a hierarchy that makes sense.
I want to circle back to something you mentioned in the roadmap, the comparisons. Because T-retriever isn't the only player in town. We talked about Raptor and ArchRag. I want a showdown.
Let's do the showdown, because there really are the 2 main rivals, and they represent the 2 extremes that T-retriever is trying to balance.
Okay, so first up is Raptor. You said that's the semantics first approach.
Yes. Raptor basically ignores the graph topology. It takes all the text from all the nodes, throws the edges away, and just clusters the text based on meaning to build its tree.
So it's great for answering questions like, what is the general theme of these documents?
Fantastic for that. But it fails spectacularly at what's called multi-hop reasoning.
Give me an example. What's a query where Raptor just falls flat on its face, but T-retriever would work?
Okay. Imagine the question is, who is the cousin of the man who wrote the book about lasagna?
Okay, a multi-hop question.
Right. Raptor looks at the text, it finds the text for lasagna, and it clusters it with pasta and Italian food. It finds the text for cousin and clusters it with family and relatives.
It's lost the specific connection.
It has severed the direct link between the specific author and his specific cousin because they didn't necessarily use similar words in their documents. It threw away the family tree, the edges, to focus on the topics.
It threw away the red string. So it can't hop from lasagna author the cousin.
It can't make the jump. Now look at the other extreme, archrag. This is structure first. It uses those community detection algorithms we talked about.
So it preserves the red string perfectly.
Perfectly. It knows exactly who is connected to whom. But
because it chops the graph into those arbitrary communities based on quotas, it might separate the lasagna book node from the pasta sauce node just because they weren't sitting physically next to each other in the library.
It cuts the semantic thread. It damages the meaning.
So T-Retriever sits right in the sweet spot in the middle.
It sits in the middle. It beats Raptor because it respects the edges. It sees the family tree. And it beats archrag because it respects the text. It sees that lasagna and pasta sauce belong together, even if they are structurally a bit distant.
And the results in the paper actually back this up.
They do. The paper tests this on a couple of benchmarks, one called book graphs, a huge data set, almost 77,000 nodes, and another called WebQSP. T-Retriever improved accuracy by over 6% on book graphs.
And in the world of AI benchmarks, 6% is massive. Usually people are fighting for 0.5%.
It is a very significant jump, and it's important to note where that gain comes from. It comes from complexity. On small, simple graphs, T-Retriever is about the same as the others. But as the graph gets bigger and messier, as the structured chaos increases, T-Retriever pulls further and further ahead.
Because that sus entropy compass shines when things are chaotic. It's designed to find the order in the noise.
That's where its strength lies. Correct.
I also want to touch on efficiency again. We mentioned the build time, that it's an offline cost. But what about the token usage at query time? LLMs are expensive to run. If I have to feed 10,000 words into GPT-4 every time I ask a question, I'm going to go broke pretty fast.
This is a huge selling point of the methodology. Because T-Retriever uses that multi-resolution search, it's incredibly precise. It finds the exact right nodes, both high-level and low-level. It doesn't need to feed the LLM pages and pages of irrelevant text just in case.
It's more targeted.
Way more targeted. The paper shows it reduces the number of tokens needed for the final generation step by up to 84% compared to flat retrieval methods.
An 84% reduction. That's not just a little better, that's a game changer for cost.
It's the difference between your system reading the whole encyclopedia to find an answer versus reading just the single relevant paragraph. It's faster, it's cheaper, and often it's more accurate because the LLM isn't getting distracted.
Okay, we are coming up on the hour, but I want to be a responsible critic here. We've been praising this methodology a lot, but what does it assume? Where does it break? What are the failure modes?
Great question. The biggest and most important assumption is right there in the name. Textual attributed graphs. T-Retriever relies very heavily on that semantic density entropy, the bell curve of meaning.
Which means the text has to be good. If the text is garbage, the whole thing falls apart.
Right. If your nodes have garbage text, or worse, no text, just IDs like user 4567, the semantic part of the compass breaks, you're back to just doing structural clustering, which we already know is flawed.
So if I have a graph of anonymous crypto transactions with no descriptions, just wallet IDs, T-Retriever is overkill.
It's overkill and likely ineffective. It needs the richness of the text to drive that catalytic effect we talked about. It needs the text to pull the bridge nodes into the right clusters.
That makes sense. The other big assumption seems to be the tree hypothesis itself.
Yes, that's the philosophical bet they're making. The assumption that a graph can be effectively mapped to a tree without losing vital information.
Because graphs are cyclic and trees, by definition, are not.
Right. The regulate and prune steps are, in a way, heuristics that are forcing a fit. They're sanding down the messy reality of the graph to fit into a clean hierarchy.
And if the graph is a total hairball, where everyone was connected to everyone else, forcing a tree structure might strip away too much nuance.
Exactly. In a highly dense, fully connected graph, the S-entropy might struggle to find any good cut. The tree might end up looking like a flat bush, just one root and thousands of leaves connected directly to it.
And then you've lost the entire benefit of having a hierarchy in the first place.
You're back to where you started. But for most real-world data social networks, knowledge bases, citation graphs, that's not the case. They have structure.
And on those, it seems to work.
It seems to work remarkably well. It suggests that even within a messy web, there is a natural hierarchy waiting to be found.
That leads me to my final thought for the day, and I want to get a little philosophical here, if you'll indulge me.
Let's hear it.
We started with the conspiracy board, the web. And we spent the last hour talking about how T-Retriever uses entropy to force that web into a neat and tidy tree. So here's the question. If T-Retriever proves that any informational graph can be optimally compressed into a tree based on this fundamental principle of entropy, does this suggest that human knowledge itself has a natural hierarchical shape? Are we building trees because that's just how computers happen to think? Or are we building trees because that's how reality is actually structured, and we are only just now discovering the math to map it properly?
That is a profound question. Herbert Simon, another giant of the field, had a theory of near decomposability. He argued that all complex systems, biological systems, societies, economies, they all evolve into hierarchies.
Right.
Because they're more stable.
Stability.
A flat, fully connected system is incredibly fragile. One small failure can cascade and bring the whole thing down. But a hierarchical system is robust. A leaf can die without killing the branch. A branch can die without killing the tree.
So maybe T-Retriever isn't imposing a tree on the graph.
Maybe it's revealing the tree that was hiding in the graph all along.
Revealing the hidden order. I love that.
It bridges the gap. It says, vector databases, you are right about meaning. Knowledge graphs, you are right about structure. But you are both just shadows of a larger hierarchical truth that combines you.
A unified architecture for knowledge. Well, on that note, we are going to wrap up. We've gone from conspiracy boards to Shannon entropy to the fundamental nature of reality itself.
Just another Tuesday on the deep dive.
Exactly. For our listeners, if you want to dig into the math, and I mean the actual formulas for psi entropy, we have linked the Way It All paper in the show notes. It is a dense read, but absolutely worth it if you're interested in information theory.
Highly recommended.
Until next time, keep untangling the web.